All right. So today is 6/14. Okay, our topic for today is the area between two curves. Okay, so before we take a look, before we start writing notes on the area between two curves, let's take a look at graphically what this looks like. We can relate it to chapter 4 when we found the area underneath a curve. So this is going to be very similar. With the area underneath a curve, your curve was always bounded by the x-axis. When we found the area beneath a curve, it was the region that we were finding was bounded by the curve itself and the x-axis. If the curve was above the x-axis, your area was positive. If the curve was below the x-axis, your area was negative. So this will be kind of similar in that sense. All right, so we're going to take a look at finding the area of the region between these two curves. Now, if we go back to chapter 4, if we kind of ignore this graph here and just take a look at the line that we have here, to find the area underneath this curve, under this line, going from 0 to 2, we would just take the integral from 0 to 2 of 2x. And it automatically would be bounded by the x-axis. So if we do that, take the integral from 0 to 2 of 2x, what we're going to get is all of this area here. If we were to take the area of the curve from 0 to 2 of x cubed divided by 2, we would get this area here. So if we want to find the area of the region between these curves, we would take the area of the line and subtract out the area of this curve of x cubed divided by 2. And that's exactly what we're going to do. So if we think about the region, so here's our region here, so we want this area here. So we're going to need to take the area of the line and then subtract out the area of the curve. And what we will have left is just this area here. Well, we already know how to do the integral. So our answer would be the area between this region would be the integral from 0 to 2 of g of x minus f of x. Now, theoretically, technically, we could separate this into two integrals. The integral from 0 to 2 of g of x minus the integral from 0 to 2 of f of x. But with our rules for integrals, we can go ahead and put these together. So basically, the way you're going to look at these is, if you are finding the area of a region with respect to x, it's always going to be top function minus the bottom function. Always top function minus the bottom function. The area of a region between two curves is always going to be positive. It'll never be negative. So we have to make a mental note of that. The area underneath a curve, if it's under the x-axis, is going to be negative. But the area between the regions, two regions, will always be positive. Now we can also look at this. So this area here is 2. So the area of the region of this curve from 0 to 2, g of x minus f of x is 2. And we're looking at this from the perspective of the x-axis with respect to x. Well, what if we were to change this with respect to y? Change it with respect to y. No, I don't want to do that. Oh. So if we look at this with respect to y, still the same graph, but now our region isn't going, our limits aren't going from 0 to 2. So notice we've changed our functions in terms of y. So it's f of y is 2y to the 1/3, g of y is y over 2. But now our limits are going to go from 0 to 4 because this is in terms of y. So, but our region is still going to be the same. So when we look at the area between the curves, it's still going to be exactly the same as we were looking at it from the perspective of x. And as a matter of fact, on your homework assignment tonight, you do get problems where they're in terms of x, and you have to change them in terms of y, and then compare to see if you get the same answer. So there's lots of practice in that sense. In any event, this is still the same curve as the last example. So the area should still be 2, whether you find the areas with respect to x or with respect to y. So if we show our answer here, so now this would be f of y minus g of y from 0 to 4, and our answer is still 2. And that shouldn't surprise you because it's still the same region. No matter which way you look at it, the area should still be 2. But when you're finding the area of a region with respect to y, it's no longer top function minus bottom function. It's going to be the function to the right minus the function to the left. So here, this f of y, that's our function to the right. And here's our function to the left. So we go from 0 to 4 with respect to y, and then f of y minus g of y. So that's a little visual. Let's see if I have a couple more. Okay, so with this one here, okay, so notice here, when we look at the area between the regions of these two curves, and we're going from -1 to 3, well, your g of x happens to be the top function from -1 to 0. But then it's the bottom function from 0 to 3. Okay, so how are we going to find that area? Because we said with this, when it's respect to x, it's top function minus bottom function. But from -1 to 0, the g of x is our top function and the f of x is our bottom function. But when we look at it from 0 to 3, it reverses. The f of x is the top function and the g of x is the bottom function. So any suggestions, Pablo? The g of x is the, what color is that? Colorblind, like tannish or mauve, I don't know, some fancy name to it. Okay, so go ahead. Okay, so if you didn't hear that, Pablo said, well, could we break this up into two integrals? So the first one would go from -1 to 0, and it would be g of x minus f of x. And the second one would go from 0 to 3, but in this case, it would be f of x minus g of x, and that's exactly what you would do. You would have to break it up into the two separate integrals and then take the sum of those. So we start off with the g of x. So it says one integral can't find this area. One graph is not always above or below the other. All right, so it's kind of showing us that there. All right, so let's go ahead and stop this. Stop it. Okay. All right, so we'll go ahead and stop that and go back to our. All right, so the area between two curves. All right, so the area between two curves, let's go ahead and get a visual of that. So let's say we have a curve F and a second curve G. And we're taking a look at the area of the region bounded by the vertical lines x equal a and x equal b. Okay, so the area is going to be the integral from a to b of f of x minus g of x dx. In this case, we know what our limits are because we're given them. Our limits are from a to b. Okay. There are going to be many cases where you're going to be asked to find the area of a region between two curves, and the limits are not going to be given to you. In those cases, you have to find the points of intersection. So where do those two curves meet? So let's take a look at an example. Okay, so we're going to say let f of x equal 2 minus x squared. And we're going to let g of x equal x. And by the way, be real careful. It's not always f of x minus g of x. If g of x is your top function, then it'll be g of x minus f of x. Okay, so don't be lulled into the fact that f is always first, because that's not the case. You have to analyze it to see which function is on top. Okay, so let's go ahead and graph this. All right. So f of x, or g of x, is equal to x. So it's a line at a 45 degree. All right, so the f of x is equal to 2 minus x squared. Well, we know that our y-intercept is at 2. Right? Okay, when x is 1, when x is 1, y is 1. When x is negative 1, y is also 1. So our graph will do something like this. So we need to find this point of intersection here. So the area of the region that we're looking for, we are looking for this area here. But we need to find the points of intersection. So how can you find points where two graphs are equal to each other, or two equations are equal? How will we do that analytically or algebraically? We set them equal to each other. So where is f of x equal to g of x? So that will give you your points of intersection. Well, 2 minus x squared is equal to x. Well, that's x squared plus x minus 2 is equal to 0. So where are your 2 points of intersection? Can we factor this, or do you guys want to use quadratic formula? You want to complete the square? Factor? So x, and it looks like, is it a plus 2 and a minus 1? Is that okay? Okay, so x equals negative 2, and x equals 1. So those are your points of intersection. So at negative 2 and at 1. So the area of this region is going to be the integral from negative 2 to 1 of f of x minus g of x dx. And that's only because the f of x is our top function. So then that's now we can go ahead and substitute in our values for f of x and g of x. From negative 2 to 1, of 2 minus x squared minus x dx. Just to kind of warn you a little bit, for this particular problem, not necessarily the case, but you're taking the difference of f of x and g of x. So this negative sign would have to be distributed to every term that would be in g of x. And oftentimes students on the AP exam, they forget that and they end up with the wrong answer. So this is just, we're going to go from -2 to 1 of 2 minus x squared minus x dx. And now it's just a matter of finding the antiderivatives and evaluating it for the limits between -2 and 1. Now, you would also be surprised at how many students mess up on the arithmetic here. So typically on an FRQ, you're going to get points for coming up with the correct integral, and usually the answer itself is just 1 point. So I've seen some crazy stuff with the arithmetic, especially when you're dealing with fractions, which in this case we are. Okay, so the antiderivative of 2, so we get 2x minus 1/3 x cubed, and then minus 1/2 x squared, and then we're going to evaluate that from -2 to 1. So that's 2 times 1 minus 1/3 times 1 cubed minus 1/2 times 1 squared minus 2 times -2 minus 1/3 times -2 cubed minus 1/2 times -2 squared. So that's 2 minus 1/3 and then minus 1/2. Here this would be -4. -2 to the third would be a -8. So -1/3 times -8 is positive 8/3. And -2 squared is a positive 4. So positive 4 times a -1/2 is a -2. So I don't know. Now what? 2 minus 1/3 minus 1/2. Do we get a common denominator? 6? So 12 over 6 minus 2 over 6 minus 3 over 6. So 12, take away 2 is 10, take away 7 over 6. All right, I got that part right. So 7 over 6, and then what about this part right here? Well, -4 minus 2 is -6. So you get -6 plus 8 over 3. So is that -18 over 3 plus 8 over 3? It's -10 over 3. So this would be 7 over 6 minus a -10 over 3. And then whatever that is. So 7 over 6 plus 20 over 6. 27 over 6. Is that right? I think it's right. I hope so. All right. Any questions on that part? That would be the area of the region between those two curves, yes. You don't think it's right? I don't know. I know I can't add. Is it right? It is? I'm not sure. Huh? Simplify, 27 over 6. So 3 goes into both, right? So how about 9 over 2? Is 9 over 2 okay? Okay. 4.5? You have 4.5? Okay. I got 4 and 1,000 over 2,000. Is that right? I don't know. Okay, so let's take a look at a couple more examples and then we'll get you started. Now, your homework is pretty intimidating. If you take a look at your homework is page 452, 1 through 55 odd. So let's go ahead and I'll get you new assignment logs tomorrow. So your homework is page 452, 1 through 55 odd, and then 72 and 75 through 78. So it's quite a bit. Now, we are actually going to be doing this section 7.1 tomorrow in class. Okay, so we're not going to do anything new. We'll take a look at specific problems. But we are going to be doing this tomorrow in class. So it's kind of like instead of getting just 1 day, second and third period on this, we're going to get 1.5 days because we're starting the lecture here and then tomorrow we'll go ahead and finish this up in class. Okay. Now you do have a 1 problem non-multiple choice quiz tomorrow, and the way the quiz is going to the way the quiz will work is basically I'm going to give you a problem. And it'll probably be with respect to x, and I'll have you find the area, then I'll have you change everything with respect to y, and then you'll find the area again to show that they're the same.
How many can we miss?
Well, it's only 1 problem.
How many can we miss?
You can't miss any. It's only 1 problem. It's only the 1 problem. Okay, let's take a look at an area with respect to y. So in this case, we will start with x is equal 3 minus y squared, and x is equal to y plus 1. So x is equal to 3 minus y squared, and x is equal to y plus 1. Okay, now we're so conditioned to looking at functions in terms of x that when we have to graph one in terms of y, it's kind of a little off for us. So what I'm going to do with this problem is we'll go ahead and put it in respect to, or in regards to x, just to take a look at what the graph would look like. So here, this is the same thing as y squared is equal to 3 minus x, or y is equal plus or minus the square root of 3 minus x. Okay, this one is y is equal to x minus 1. All right, so what would the graph look like? Would it be a semicircle? I don't know. Maybe. So let's go 1, 2, 3. So we still need points of intersection. So the y equals x minus 1. Well, we do know that our y-intercept is at -1, and our slope is 1, so we go up 1 over 1, up 1 over 1. So we can go ahead and take a straight edge and draw a line through those points. Might have lost the pencil. There we go. Okay, so we can take a straight edge and draw a line through those points. Okay, so here is the graph of x is equal y plus 1. Okay, so now we need the graph of x is equal 3 minus y squared, or y is equal plus or minus the square root of 3 minus x. When x is equal to 0, when x is 0, y is the square root of 3, right? When x is 0, y is this, about how much is the square root of 3? Like 1.72 or something like that. So it's going to be somewhere around here. You got a question? Well, when x is equal to 0, y is equal to that. Thank you. I guess that makes sense. I'll have to edit that out of the final cut. Okay, so when x is equal to 0, it is the y that's equal to, well, when x is equal to 0, y is going to be positive square root of 3, and it's going to be negative square root of 3. So the negative square root of 3 will be down here, and then a positive one will be up here somewhere. Okay. Now when y is 0, when y is equal to 0, I don't know what x is. I'm lost. I'm lost around here. Okay, so y is equal, so how would we, yeah. Well, how about when x is 3? When x is 3, y is 0. That's what I'm looking for there. All right, so it's going to do this. And this. Okay, so it's going to do that. So we need to figure out where these two intersect. At what y values? Here and here. What's our value for y? But we do see which function is our rightmost function and which function is our leftmost function, right? So here's the function that's on the right-hand side. Here's the function that's on the left-hand side right here. And the region that we're looking for is this region here. So that's the region between. All right. Let's go ahead and find our points of intersection. So points of intersection with respect to y is going to be 3 minus y squared is equal to y plus 1. So we set the two functions equal to each other. Or I should say two equations. So that's y squared plus y minus 2 is equal to 0. Is it y squared minus 1? Because I added y squared to both sides, and then I subtracted 3. All right, so now we have, looks like it's going to be y, and then plus 2 and minus 1. So y is equal to negative 2, and y is equal to 1. So your limits are going to go from negative 2 to 1. And our area is going to be the integral from negative 2 to 1 of 3 minus y squared minus y plus 1 dy. And here's what I was talking about a little earlier. This negative sign needs to be distributed all the way through. So that's the integral from negative 2 to 1 of 3 minus y squared minus y minus 1. dy, or the integral from -2 to 1. 3 minus 1 is 2, so 2 minus y squared minus y dy. And then at this stage, it's just a matter of finding the antiderivatives and plugging it in. So we'll stop there and let you finish that.